pressure gradients. Then we have the exchange of O2 and CO2 between the lungs and the pulmonary capillaries. What drives that? Pressure gradients do. Did we do this last week in lecture? Wednesday people? Wednesday people, have you seen this?
No, I don't.
Okay. All right. Then the oxygen-rich blood goes through the systemic system, all of the systemic pulmonary veins, through the left side of the heart, through the systemic arteries, until we get to the systemic capillaries, which are site of exchange. Oxygen moves down its pressure gradient out of the systemic capillaries into the tissues. CO2 moves down its pressure gradient out of the tissues into the systemic capillaries. So then when I get at the end of this, I have my systemic venous system that has oxygen-poor blood, goes to the right side of the heart, to the pulmonary arterioles, where we go back to the pulmonary capillaries. Again, CO2 moves down its concentration gradient out of the, down its pressure gradient out of the pulmonary capillaries into the lungs. O2 down its pressure gradient out of the lungs back into the capillaries, and we start over again. Okay. All right, so. Okay, I'm sorry that that's cut off. So this is forces for pulmonary ventilation. So air moves in and out of the lungs by what we call bulk flow. Bulk flow means whichever way the pressure is higher, things are going to move in general that way. The pressure gradient drives bulk flow. Things will move from a high pressure to a low pressure, whether we're talking about volume of blood when we're looking at the cardiovascular system, which is that part of chapter 14.5, whether we're looking at air here in the respiratory system, or whether we're looking at plasma, specifically serum, in the urinary system. Okay? Inspiration, the process of inspiration, also inhaling, same thing, is that air moves into the lungs, bulk flow, because the pressure in the atmosphere is higher than the pressure in the lungs. I can say it the other way, the pressure in the lungs is lower than the pressure of the atmosphere, and air moves down its pressure gradient. Expiration or exhaling, again, air is going to move down its pressure gradient. So in order for us to exhale, the pressure inside the lungs has to be higher than the atmospheric pressure. Does atmospheric pressure at a given sea level change? No. Pressure at a given sea level stays the same. If I go up to the mountains or I go down in the ocean, it changes. But at a given sea level, the pressure, the atmospheric pressure is the same. So when we're talking about movement in and out of the lungs, it's the lung pressure that has to change, not the atmospheric pressure. Okay, really quickly, and we're going to look at these in more detail as we go through. And again, Monday people, I know you saw this, but I'm going through it more quickly. Atmospheric pressure. P is always going, that capital P in italics is always referring to pressure. PATM is the pressure of the atmosphere at any given latitude. Intra-alveolar pressure is the pressure of the air inside each alveolus. Okay? Intrapleural pressure is the pressure in that pleural cavity between the lung and the thoracic wall. And transpulmonary pressure is the difference in pressure between the pressure inside the alveoli, which is the alveolar pressure, and the pressure on the outside of that alveoli, which is the intrapleural pressure. So here I have my wall of the alveolus, okay? The alveolar pressure is pushing from the inside out. The intrapleural pressure is pushing from the outside in. Who wins?
The greater pressure.
Whichever is greater, right? So if the alveolar pressure is higher than the intrapleural pressure, then the alveoli expand. If the alveolar pressure is lower than the intrapleural pressure, then the alveoli contract. Okay, makes sense?
Mhm.
Okay, so atmospheric pressure decreases as altitude increases. So again, just to clarify, from the edge of our atmosphere down to the ground, there is a column of air. And that column of air, even though we don't think about it, has weight. And that means it has mass, which means it exerts pressure. Okay? The pressure exerted by the column of air from the edge of the atmosphere to the ground at sea level is identified as 1 ATM, or 1 atmosphere. If I go from sea level up to 4,000 feet, does it make sense that my column is shorter? Right? If I go from the edge of the atmosphere down to sea level, it's this big. If I go up 4,000 feet, my column is shorter. So, atmospheric pressure decreases because my column gets shorter, the more my altitude increases. And conversely, if I go underwater, although my atmosphere column doesn't change, what gets added? A column of water, right? So if I have my column of atmosphere and then I go diving, when I get down to 100 feet, I've got that column of atmosphere, plus I have 100 feet of water and the pressure that exerts on me as well. So it increases underwater, and it should make sense that the pressure of the water is a bigger pressure than the pressure of the air, which is why divers have to be so careful, because going down 15 feet underwater is very different than walking upstairs 15 feet. Okay? So when we talk about the pressures in the lungs, the intrapleural pressure, the alveolar pressure, the transpulmonary pressure, which is related to the alveolar and the intrapleural, we're all talking about them relative to atmospheric pressure. Okay? So we're going to say that that atmospheric pressure is 0. We talked about this once before. We're going to randomly assign it at 0. Think about it like tearing out a balance, right? Whatever pressure is on that balance, you hit tear and it says, okay, whatever this is 0, right? Okay, so what pulmonologists have done is they've said, okay, what atmospheric pressure is, we're calling that 0. That's our baseline. So that when we then talk about intrapleural pressure, alveolar pressure, the difference between those two, which is transpulmonary pressure, we're all talking about relative to that atmospheric pressure, which we're tearing out at 0. Okay? Okay?
Okay.
Okay, excellent. So good, Sarai. All right. So, the intraalveolar pressure, that's the pressure inside each alveolus. Pressure of air inside the alveolus. It's again given relative to atmospheric pressure because atmospheric pressure stays the same. Okay, so it will be either less than atmospheric or greater than atmospheric. Okay, if it's greater than atmospheric, it's assigned a positive value. If it is less than atmospheric, it is assigned a negative value. Okay, what that pressure is, that intraalveolar pressure relative to atmosphere, depends on what's going on with the lungs. If I want to inhale air, the pressure in the alveolus has to be less than atmospheric pressure, so that air will move from the atmosphere in, which means the pressure during inhalation or inspiration inside here is going to be what? It's going to be negative, because it has to be less than atmospheric, which is 0, if air is going to move from the atmosphere into my lungs, down its pressure gradient. Conversely, during expiration, if we want the air to leave our lungs and go out, then the pressure inside here has to be positive, higher than atmospheric pressure, in order for the air to move down its pressure gradient out of the lungs and into the atmosphere. So, because the atmospheric pressure at any given altitude is the same, what drives which way the air moves is the change in intraalveolar pressure. If the intraalveolar pressure is less than atmospheric pressure, air goes into the lungs. If the intraalveolar pressure is higher than atmospheric pressure, air moves out. Okay. And when they are equal, there's no net change. Realize that if it goes from higher than atmospheric to lower than atmospheric, I have to have a moment where they are equal. And when I say a moment, I mean a fraction of a second. Okay? And if I'm going to go from lower up to higher, again, I have to have a moment where they are at equilibrium. Okay. The intrapleural pressure is, if we look here and we look at this space between the lung and the chest wall, remember the part of the pleural membrane, the part of the serous membrane, and pleural because we're talking about lungs. The part of the serous membrane relative to the pulmonary cavity that touches the lung itself is the visceral pleura. The part of the serous membrane that touches the thoracic cavity is the parietal pleura. Again, visceral because it touches the organ, parietal because it touches the cavity wall, pleura because we're talking specifically about the lung. And in between it is where I have my intrapleural space, okay? And that's where I have my intrapleural pressure, okay? So remember, inside here I've got all my alveoli. And those alveoli are being influenced by two things. They're being influenced by the atmospheric air, and they're being influenced, or the pressure of the atmosphere, and they're being influenced by the pressure in here. Okay? So, this that made everyone go, what? Okay, I've got, I'm not kidding, I've got like 300 slides on this. It's all animations. All right, so I'm starting here. I know this looks like a water bottle, one of those big, okay? What it represents is the chest wall, and instead of having two lungs inside with a billion alveoli. I'm just showing one single alveolus. But remember, there are hundreds of thousands of alveoli per lung. And if you review the anatomy, those alveoli are connected to each other through alveolar pores in order to make sure that the pressure is equalized throughout the lung. So here, for simplicity, my entire lung is represented as this single alveolus. My intrapleural space, which we know in reality is just this little space, is represented by all of this space because I need it as things move. So, out here is the atmosphere. This is intra-alveolar, and this is intrapleural. These are my thoracic cavity walls. This is my diaphragm. Okay? So, we start with air molecules. Okay? The ones that are green are what I call free-flowing, meaning they can be exchanged between the atmosphere and the alveolus. The ones that are orange are the ones that are inside that intrapleural membrane. And that intrapleural membrane is a closed system. Okay? So those orange molecules do not change in number because this is a closed system. The green move because the connection between the alveolus and the atmosphere is an open system. Now, I'm going to bring this concept around, excuse me, yet again. When air molecules move into and out of the alveolus, is that going to make a difference in the pressure of the alveoli?
Yes.
Yes. When molecules move into and out of the alveolus, is that going to make a difference in pressure in the atmosphere?
No.
No. Why?
Atmosphere doesn't change.
Ocean pool, right? Atmosphere is the ocean. Alveolus is the pool. Okay? Or was it Frank who said air, atmosphere, right? That's literally what it is right now. So all I've done now is add air molecules, showing you that these that are green are able to move between the atmosphere and the alveolus in both directions, and these that are in the orange are in that intrapleural space, and that number is set. So we're going to start out at equilibrium. Okay? And that means if I am at equilibrium, that the pressure inside the alveolus compared to the pressure in the atmosphere is what? They're the same. They are equal. And we're going to say, just so we have some place to start, that this is the equilibrium that I've reached after I'm done exhaling. So, right? No air entering, no air leaving. So that's the equilibrium after I've just exhaled. So what we're going to go through now is from here through back to there. That's what we're going to do stepwise. Okay, so we have equilibrium after we've exhaled. So what do we want to do now?
Inhale.
We want to inhale. So after equilibrium of exhalation, then what's going to happen? We actually start with the anatomy. What happens? My thoracic muscles contract. Okay? My external intercostal muscles contract. My external intercostal muscles, their origin is the superior rib, and their insertion is the rib immediately inferior. In other words, when they contract, they pull the inferior rib up to the superior rib. So rib 12 pulls towards 11, 11 pulls towards 10, 10 to 9. End result, it lifts your rib cage up and out. You can all see that if I take a deep breath. Watch. Right? You can see that. Put your hand on your chest. Close your eyes. No other distractions. Take a deep breath. Feel your rib cage move up and it expands out to the sides. Okay? What causes that to happen? Contraction of those thoracic muscles. We've got another big player in this. What else contracts? The diaphragm does. And this is showing the diaphragm relaxed. When the diaphragm is relaxed, it is arched and it is up into the thoracic cavity. When it contracts, what does it do? It flattens out, right? So when we contract our thoracic muscles and we contract our diaphragmatic muscles, well, that causes our thoracic cavity to do what? Gets bigger. Okay, so we're going to look at how it affects that intrapleural space. And I'm going to focus on just the intrapleural space for right now. That's why I took the green dots away. Okay. Right now, I'm just focusing on this. Okay. So, because we're talking about the movement of air molecules, we're going to go to your chemistry favorite. PV equals nRT. Yeah, see, that's the expression I look for most people. Right? All right, what's P? Pressure. What's V? Volume. What's N?
Constant.
Number of moles. N is the number of moles, and it's always written as a lowercase n, by the way. Capital N is newtons. It's an entirely different thing. What's R? Yes, but what do we call that?
Constant.
That's the gas constant. Guess what its value is? Constant. It doesn't change. Okay, what's T?
Kelvin.
Temperature. Okay, so pressure, volume, number of moles, gas constant, and temperature. Okay. If we change the size of our cavity, is our volume going to change? Yes. Are volume and pressure related? Yes. So if we change the volume, we're going to change the pressure. Okay. Does my gas constant change?
No.
Nope. Does my temperature change at a given moment? No. So we said my pressure will change because my volume changes. We said N is the number of moles, R is our gas constant, and T is our temperature. So, when we contract our thoracic and our diaphragm muscles, then, someone said earlier, what's going to happen to this?
Increase.
My intrapleural space is going to increase. It's going to get bigger, right? So, what does that mean? That means my volume increases, right? So now my volume has increased, right? And we're going to look at our NRR and our T, okay? What did we say N was? Moles. Number of moles. Has the number of moles inside here changed? No, why? Because it's a closed system. Has my gas constant changed? Because it's constant. Has my, in general, has my temperature changed? No. So these are all eliminated, right? And so if I eliminate all of these, then I'm focusing just on pressure and volume. So if I'm focusing just on pressure and volume, as volume increases, pressure decreases. They are what we call inversely related, right? Pressure represents how many molecules are bouncing against our container, whatever it is, at a given unit of time. If I increase the size of my container, it takes longer for some of those molecules to reach the edge. So I have fewer collisions per unit time. And since collisions per unit time is what pressure represents, then if I increase my volume, I decrease my pressure. Okay. So notice my molecules spread out. Okay. Everybody good with that? Okay. So when we're looking at the intrapleural space, it is a closed system. The number of moles doesn't change, the gas constant is constant, temperature doesn't change. So in my intrapleural space, the only two variables that I need to consider are pressure and volume. As the volume increases, pressure decreases. As the volume decreases, pressure increases. Okay? All right. Now, let's look at our alveolus. Okay. And let's follow this stepwise. Because my thoracic muscles and my diaphragm contracted, this volume got bigger, larger, which means the pressure here decreased, right? If the pressure decreased here, and for a moment, this pressure, the intraalveolar pressure, stays the same, then if I have a lower pressure here than here, what's that going to do to my alveolus?
To expand.
It's going to allow it to expand, right? Because before that, these pressures were equal when I was at equilibrium. But when this got larger, this pressure decreased. It decreased less than the pressure that was inside my alveolus, allowing my alveolus to expand into that decreased cavity. So, alveolus bigger. Okay? So, I'm not looking at the intrapleural space anymore, because now we're going to look between the alveolus and the atmosphere. So I took out our intrapleural molecules, and now we're just going to focus on the molecules in the air and the alveolus. So, when my alveolus gets larger, what's going to happen to the pressure inside my alveolus? It's going to decrease. And if the pressure inside my alveolus decreases, it is less than at atmospheric pressure, because remember, when we started out at equilibrium, the pressure inside the alveolus and the pressure inside, or in the atmosphere were the same. Through increasing the size of the thoracic cavity, therefore decreasing the pressure in the intrapleural space, therefore increasing the size of each alveolus, therefore decreasing the pressure inside of each alveolus relative to atmosphere, that causes air molecules from the atmosphere to move into the alveolus. So the driver for all of this is the contraction of the thoracic cavity and the diaphragm. So now let's go back to our PV equals nRT. This one's in orange because it was while we were looking at the orange intrapleural space. That one's pink because we're calling the alveolus pink. Okay. So let's go back to neutral. At neutral, we are again going to look at all of our variables. So when my alveolus increased in size, my volume increased, right? If my volume increased, then, well, wait a minute. When we looked down here before, we didn't look at N, at R, or at T, right? Okay. But when we look at this now, when our alveolus got bigger, we saw that our volume increased, therefore our pressure decreased. And when our pressure decreases, what's going to happen? Air's going to flow in. Well, hold on, let me go back. Let me go back a minute here. No, not that far. Okay. So, let's start here. I have air in my alveolus, right? My volume here increases, so my pressure here decreases. My pressure here decreases, so my volume here increases. My volume here increases, so my molecules spread out. Come on. And when my molecules spread out, the pressure decreases, right? When that pressure decreases, it's now less relative to atmosphere, which means air moves in. Because this is an open system, N, the number of moles of air, now comes into play. Okay, and this is the first time, let me just finish this one. This is the first time we've dealt with an open system. So here, we were looking at pressure and volume. One increases, the other decreases. Now, for the first time, we're looking at 3 variables. We're looking at pressure, volume, and number of moles. So because the pressure inside my alveolus decreased, because the volume of my alveolus increased, because the pressure in my intrapleural space decreased, because the volume of my intrapleural space increased. End result, because the pressure in my alveolus is less, the number of moles increases, and air comes in. Okay? So far makes sense. Okay? So, when we're looking intrapleural, we have 2 parameters we have to look at, pressure and volume and their interrelationship. When we look at the alveolus relative to the atmosphere, now we've not only got to look at pressure and volume, but we've got to look at number of moles. And this is tough because we're used to being able to say, oh, if this increases, this decreases. Or if this decreases, this increases. Now we have to say, well, if this and this do this, how does this one change? Well, what if this does this and this does that? So it gets more complicated. All right, so I'm going to stop. I'm going to pick this up in lab today. Hopefully somebody has figured out how I can record this